Hey everyone, welcome back to part 2 of the MCQ series. In this video, we are going to continue exploring some really important concepts from trees and heaps to algorithms like Delmin-4, topological sort, and more. If you haven't watched part 1 yet, make sure to check that out. We covered a lot of foundational ideas there. So let's begin. So the first topic that we have in our list is maximum sliding window. And as you may see, we have a total of 1, 2, 3, and 4 approaches. So one is the naive approach, that is the brute force approach. Then next is the self-balancing tree, that is the tree cell. Next is using max heap, that is priority queue, and the last is tech. The most efficient answer will be given by tech. Okay, make sure you remember that most efficient answer will be given by tech. Now in this scenario, if an array is given of this sort, okay, and the window size of 3 is given. So MCQ problem could be like on first step, on window 1, what will be the maximum element? That will be 3. Second window 3. Third window 5. 5, 6, and 7. So this would be an option that you have to take, or they will specifically they ask you a window number, supposedly 1, 2, 3, or like 0, 1, 2 of that indexing, either 0 based or 1 based. Now coming to the program, so this is the most efficient algorithm that we are using. The tree set over here, it will have n log k time complexity and space complexity of k, not n plus n minus k plus 1, because we are including the tree set as the space complexity and not the map array, because this is the input, not the helper space we are using. So don't get confused. It's only k and k because of tree set being used. It keeps a track of top k elements and then gives us the maximum out of them. So these are the other approaches and corresponding time complexity and space complexity. And this is also a very important part that could be asked in an MCQ problem. So give it a glance. Okay, moving ahead, the next topic we have is recover the BST. Problem statement goes like we have been given BST, that is binary search tree. And as we all know, the in-order traversal of a binary search tree gives the sorted ascending order of elements. Now, in case one or two, that is particular two elements are swapped, so the binary search tree will be not a correct binary search tree, and the in order would be not the actual ascending order. So what we have to do, we have to find the two elements that are swapped and kept at wrong positions, and we have to swap them back to get the actual ascending order. That's how the problem goes, like recover the beast. So we have to get back the actual PST. Now, coming to the approaches, so we have the in-order traversal, as I mentioned right now, using the two-pointer approach, and next is Morris traversal. Now, why we have come to the point of Morris traversal is that in in-order traversal, a lot of space is being used, a big of n space is being used, as we are storing the nodes and then finding which are the two nodes that are swapped and getting back them to the actual position. But over here, the extra space is used, and most of the time, space is not the concern. But if we use this approach that is called Morris traversal, so note it point, it is a very important point over here, that if we are asked to solve the problem of recovered BST with constant scale, what approach we are trying to use is called Morris traversal. If you want to learn more about this, you might read an article or so, or check on YouTube for some reference material. Okay. So next we have use of tree. We have a total 6 varieties over here. Left view, right view, top view, bottom view, horizontal view, and vertical view. As the name suggests, that is the answer, that is the point from where we are using the tree. So coming to left view is from leftmost end for each level when we are doing level of the. So from left to right, we say index is increasing 0 to n minus 1. So the 0th index at each level is the answer node that we are including in the left. Similarly for right view, it's I equal to side minus 1 when considering the index increases from left to right. But in case we do opposite point of view, that is we say for each level we are traversing from right to left and the index starts from 0. So the rightmost node at index 0 is coming in the right view answer. For top view, a new concept is being introduced, that is horizontal distance. And for a root, we say the horizontal distance is kept as 0, which is an integer value. And for each left side, we do a minus 1 of the parent horizontal distance and plus 1 of the parent horizontal distance. That's how we calculate horizontal distance HV for each node of the binary tree. And whichever HV, whichever node for a unique horizontal distance occurs first in the hash map, that is the node comma, or we can say key is the horizontal distance and the value is node. That is coming the answer of top view. Opposite to this is the bottom view. That's the last reference of a horizontal distance corresponding to a node. So supposing two nodes have the same horizontal distance. So the second node coming in the hash map is the one that will come in the bottom view answer. Coming to horizontal view, that is basically breadth first search for BFS traversal. So that is level order traversal. And next is vertical view, that is from left to right, it creates sticks, that is the vertical lines. So whichever node comes in the same stick is considered in the vertical view answer. For these views, we have these kind of space constraints. And if you keep a glance for these, in the left view, I get a recursive for every program you can do a recursive approach. but it's better to use iterative approach for these programs. It's very easy and simple to understand. Coming to time complexity, it's big of n for almost every program, but in the top view we are using hash map or pre-map basically, so n login. Similarly, in bottom view also pre-map is being used, and in vertical view also. Okay, do check the vertical view program and practice cycle code. This is the most expected program for any competitive exam of SIP. And to give a glance at the notes, these could also be asked one way or the other. Moving to the next topic, that is boundary traversal. Now, this is the next topic in the tree program again, and boundary traversal is done in a way that first we travel from root node to the leftmost node, okay, and then from leftmost node we go to the rightmost side in the leaf direction, that is the horizontal direction. Then we reverse back to the root node from the rightmost root node to the root node. That's how the answer is. But remember not to repeat the node. That is, first we'll reach the root node, then we'll go leftmost end, then we'll go rightmost end in the leaf side, and then we'll go topmost to root minus one node in the rightmost reverse direction. Remember the reverse direction. Okay. Time and space is obvious, big of n, big of h. Now, in case it's a unbalanced tree, okay, skewed tree, so this can also be log n. Log n for balanced tree and big of n in the first. Okay. So this is a simple program. You have to print the boundary nodes of the binary tree in the anti-clockwise direction. This is the pointing motor. Because if you see, first we're going the leftmost end, then leaf is rightmost travel, then to the back to the root. So if you think from a clock point of view, so this is an anti-clockwise direction movement. Okay. So this is a probable question. Coming to the next, that is BFS and DFS. The most common question that anyone could ask you at any point of time is that for breadth search, that is BFS, the data structure used will be Q, and the principal of Q is called FIFO, first in first out. Similarly, in comparing, so DFS will use stack, and stack is FIFO, last in first out. Now, BFS is a breadth first traversal, or same we can say as level order traversal. Okay. And in BFS or DFS, we go for two simple points that we have to cover: is visited and not visited. Once a node is visited, we take that as pause in visited Boolean array, and next time we are not visited. That's how we change each node once in a simple traversal. That would be best first search, that is level order for depth first, where we go first in the depth and then return back. That means we will back to the unvisited nodes. Now, these are the simple points that you can give a glance. Now, over here, very interesting point is that for an unweighted graph, DFS traversal produces a spanning tree, but not a minimum spanning tree. And for a minimum spanning tree, the approach, the algorithm that we use usually is Prince and Crusher's algorithm. In case of Crusher's algorithm, we put the edges in descending order and then take into consideration one by one. And in Prince, we start from a source node and then explore its neighbors based on minimum distances. Okay. BFS could be used to detect cycles. Now, this can also be used. BFS can be used to detect cycles as well. Okay. But the most important part of BFS is used to shortest path, minimum spanning. Okay. Fourth focus, I got cycle detection. So for BFS and DFS, we can do cycle detections using the approaches. BFS can be used for topological sort as well as BFS can be used. So when we are coming to topological sort, we'll discuss it better. BFS can be used to test if graph is bipartite. So these are some important points that you can keep into consideration from MCQ point of view. Moving ahead. Coming to the time and space complexity for both BFS and DFS, we have beta C of time complexity and big of V space complexity. Because we are traveling each vertex, each node once, so we'll store it somewhere and we'll print it. If we are printing, it will be big of 1, but if we are storing, it will be big of V. And why is V plus E? Because if we have a adjacency list, so we're traveling exactly to each vertex and each edge, so we have V plus E time complexity. Moving ahead. Next we have winner tree. And it's basically an application of tree data structure. But simply we inverted it. Now the winner tree has a simple concept of tournament tree, selection tree, we can call it the winner. And over here we have some players, and after some matches, after some rounds, we have to say who is the winner. Vice versa, this will be also as the loser tree. So a winner tree or selection tree will have 3 leaf nodes or external nodes and T minus 1 internal nodes. This would be the winner tree or loser tree. So this is a type of tree given. So for the winner tree, for the elements is 10, 2, 7, 6, 5, 9, 12, 12. How is it done? This was the tree given to us, and we had to find at each point who is the winner. So over here, 10 and 2, 2 is the winner. So this is basically a winner tree for minimum element. Similarly, this would be also for maximum element. So this would be for other winner. Over here, the minimum element is 2, over here 6, minimum element is 2, and then coming to the right, subtree 5, 1, 1, and above 10, 1. So the final answer is 1. So 1 is 7. So the time course space function will be n for obvious reasons, because we are traveling to the entire tree and then we are storing some n players in an order where the 0 to next 0 is the winner. Okay, moving ahead, we have Bellman code. Now, what is Bellman code and why we did not consider G-star algorithm? Though over here we can see shortest path into conversation. So the thing was, G-star algorithm fails when we have negative edges or negative weights. There comes into victorization, that is Bellman code. What Bellman code does is that it's a single source shortest path algorithm and it also handles negative edges. Okay. So that's a very important point. And the next thing is that it uses Bellman programming approach. It can handle negative edge weights unlike G-star algorithm. Hydrated realization is the same as we do in G-star algorithm. It can detect negative cycles. And the use case is that where G-star algorithm fails, Bellman code comes into consideration. It's a verticile algorithm for solving single source shortest path problem, and this can also be used to find if a graph has a cycle or not. Okay. Coming to the time complexity, it's weaker, not as efficient as G-star, but for root force point of view, it's a good time complexity, and it will also handle negative edges. Okay. And the space complexity is B because we are storing the answer. Okay. Rather if you are painting into one. This is a simple comparison between G-star algorithm and Bellman code. You can give a glance. Most of the time, whenever Bellman code is taken into consideration, or when we are talking about Bellman code, G-star algorithm comes into picture automatically, and you could also be asked to use it to one or the other based on the comparison. So you must give a glance at this. Moving ahead, we have topological sort. And the very important problem that would be asked for any question is that some input will be given and then they will ask, apply this algorithm, tell which is the correct output from the MCQ series. So you must practice. Grab some article or some YouTube video and see if a graph is given, how you will apply depth first search to find your topological sort answer, or Khan's algorithm, that is depth first search to find your topological sort answer. Do give it a practice, it's very important. Otherwise, you won't be able to solve that numerical in the exam. As you may have read it, topological sort is a linear ordering of the vertices of dialectic acyclic. So the point is that if a cycle is there in the graph, topological sort will fail. So the first initial requirement is that it should be dialectic as well as acyclic graph. Okay. which will give an ordering of the vertices. So when we written the word ordering, you might take into consideration of an example that is course scheduling. So if a course is being scheduled, that should be done in a sequence-wise in an order. That is, next is dependencies. It considers if task B depends on task A, then A comes before B in the topological order. Okay. Again, we have two approaches using BFS and using BFS. The easier one which I prefer is the BFS approach, that is the Khan's algorithm. And this is a very important point, that is we can have multiple topological sorting answers. Okay. So it's important to note that at this graph we have more than one valid topological sorting. The crucial aspect is the relative order of vertices connected by diagonal acyclic graph. H. So the sorting follows systematic way to order vertices of diagonal graph, reflecting the dependency to most in the natural and meaningful manner. Okay. So you must be clear about the problem statement, the example inputs and the output that will be coming using that order. Maybe any more. Next is cycles introduce ambiguity, defining a linear order. So if there are cycles, the sorting, I have an issue, I won't get an answer. This is the one I was talking about, that is the Khan's algorithm using depth first search. Coming to the next, we have heap sort. That was an application used over there in Minute. So this is a comparison-based sorting algorithm, like merge sort, quick sort, bubble sort, insertion sort, and many more, predict sort. So over here, an important point is that it's an unstable sorting algorithm. It's an in-place sorting algorithm. It has a time complexity of n log n, similar to quick sort or merge sort. And remember, quick sort can be used faster for smaller datasets, and merge sort uses additional memory in place sorting, which means it does not require additional memory for sorting. Okay, so space complexity used over here is big of one since it sorts the input at in place. Now the question that would be asked is that which one is a stable algorithm? Merge sort, quick sort, or deep sort, or none if you will. So the answer is either of merge or quick sort. So the answer will be merge sort over here. And even bubble sort, selection sort, counting sort, these are also stable ones. That is, it keeps a track of the relative ordering of the elements and do not remove them from order. So that's a very important thing. And when we are building a max heap, that is heapify function, that's time density is big of n. When we are extracting the maximum element from heapify, we take log n time property. So overall time density of heap sort is n log n, n for heapify and log n for extracting the root element. Moving ahead, we may give a glance at the code. Next, we have k-array heap. So, as we have seen previously, heap sort, where we were building a heap using heapify function and big of n time complexity. Over here, k means we can have more than two children. When we say binary, we say two children. When we say k-array, we can have k children. So for each node, we'll have array of children. Okay, remember the promise, array of children. This is commonly said as B array, that is B children, K array, K children, and heap. So that is a priority to data structure, and so when heap signifies over here and everywhere else. Instead of two children, we can have K children, repeating the same. Now again, we can have two varieties, that is max K array, min K array. Now these points are very important to remember. Parent of the node at index I, except root node, data point, is located at index I minus 1 by k. Next is children of the node at index I will be at ki plus 1, ki plus 2. Similarly to binary tree when we say 2i plus 1, 2i plus 2. 2i plus 1 is the left node, 2i plus 2 is the right node. Over here we say ki plus 1, ki plus 2, ki plus 3, and so on up to k. And the leaf node of the heap of size n is located at index n minus 2 by k. So other point is that it's nearly complete binary tree. Okay, nearly complete. Next is TP5 up operation is used. TP5 down operation is used. Insertion TP5 up, deletion TP5 down. Okay. Coming to the next, we have binary heap, and most of the people won't ask you programs for binomial heap or k-array heap because it's very complicated. But competitive platforms like CodeChef, CodeForces, they can include such questions. Okay. Coming to binomial heap or Binomial trees in general is an extension of binary heap. Here we have two operations in general, that is union and merge operation. So we'll have a lot of trees. At each node we'll have some tree. So when we are combining them, so we are using a merge operation. When we are combining a bunch of trees, we are using a union operation. Next point over here is that if a binomial tree has k nodes, then it will have 2 power k. This is the point which I am saying, that a binomial tree of order k has exactly 2 power k nodes, depth as k, and exactly phi of k comma I, that is combinations ki nodes at depth I for I 0, 1 to k. And the main operation in binomial tree is union and merge operation. Next is insert, get min, and so on. These all usually have login time density. Okay, moving ahead. You can also give a glance at the theoretical aspect of the previous topic. Coming in next, we have Tiles algorithm. Now, we have seen Dijistra's algorithm, we have seen Bellman-Ford, and this is next Tiles algorithm, which also used for shortest path problem. So you may think, why was this third algorithm brought into consideration? So again, the thing was time complexity. It was not that much good for smaller waves, coming to point. So when we are having only small waves, then this algorithm works very well and has a time complexity of v plus e cross max wave and space complexity of max wave cross v. Okay. What we do basically is that we use a bucket data structure over here. So bucket based approach, we can say like that. And at each bucket, we put nodes which are at same distances. And that's how we keep on relaxing, as you may see over here. The relaxation part, same in the Vista also we do relaxation. In Bellman Food also we do relaxation. That is the common aspect in all of them, but have different time densities. So that is how we can compare and we can think of which algorithm to use in particular point of view time and in a situation. So bucket cluster is used and each bucket signifies nodes at same distances. We move from left to right until we reach a bucket, non-empty bucket, and then we pick up the topmost element. So we use this, we use queue to create list of buckets. Thank you. And if you want the next part to come up soon, do give a like, share, subscribe for obvious reasons. अपना प्यार बरसाओ तो नेक्स्ट वीडियो जल्दी से लाते हैं, ठीक है? हमने टाइम निकाल के आपके लिए बनाया है. It took me a lot of time to first combine the topics into the PDF in the Word document and think what to write. So yes, take a moment, like it, subscribe to the channel so that I can bring the next video. I get motivated from your subscriptions and likes. Do keep a comment if you like and this helps you in the upcoming exam. Thank you once again. Bye.